Texas, my heart, shining through the dark.
Okay, y'all, today we are talking about equations of polynomials.
Texas, my truth.
I would like to start off by talking about polynomial standard form. This is kind of a great introductory form for polynomials. Because it helps us kind of see what's going on. So the standard form of a polynomial looks like this, and it looks pretty funky. Don't let it freak you out. When we look at a few examples, I think it'll be helpful. Okay, so what in the world is going on here? So all this is saying, this is the general form of a polynomial. Each term has this sort of general structure of some coefficient, a with some subscript, times x to the n. So we have this coefficient that's some real number, then times x to the n. The subscript here just matches the coefficient with the term with this exponent. The term with the exponent n has the coefficient a sub n. The term with the exponent 2 has the coefficient a sub 2, etc. That's how this general form works. Why does it look like this? Well, polynomials can have any number of terms, right? We don't know if there's one term, we don't know if there's 3 terms, or if there's 27 terms. So we are saying for however many terms there are, this is going to kind of give us the outline of what it's going to look like. Why does a sub 1 times x not have an exponent? If a sub 2 belongs with x squared and then the next term is a sub 1 times x, what's the exponent? If we don't have an exponent written, then it's just 1, right? Because there's one x there. So there's kind of a silent 1 on that a sub 1 term. Similarly with a sub 0 is a coefficient, but we can think of it as having x to the 0 written next to it, because what's anything to the 0? It's just 1, right? Even those last 2 terms kind of fit into this structure. So a couple of examples of a polynomial. I'm going to leave a little bit of space so we have some room here. F of x equals 2x cubed plus x squared minus 3x plus 4. This is a pretty normal polynomial. We've got 4 terms. So n is 3 here, right? A sub 0, the constant term, is 4. A sub 1 is negative 3. A sub 2 is, there's nothing written. So is it 0? No, if we had 0 multiplied by x squared, then it would be all 0, so the term wouldn't be there. So the coefficient, when we have nothing written, is 1. And here, the coefficient a sub 3, right, because it's on the x cubed term, is 2, right? And here, n is 2. Okay, let's look at another. Let's say we have g of x equals, again I'm leaving some space, 3x to the 70. Just making up kind of a crazy example. This is also a polynomial. It doesn't have every term listed out like the previous one does, but it has 2, That's okay. Sometimes we have missing terms. That's totally fine. We're missing all of the terms between 1 and 70, right? Also missing a sub 0, right? We're missing our x to the 0 term. That's totally fine. Sometimes that happens. It's still in standard form. As long as they're written with decreasing order, right? So 70 is larger than 1, clearly, so 70 comes first, then it's in standard form. Okay, so I want to kind of point out a few things. The first one is this guy, this a sub n. A sub n is what we're going to call the leading coefficient. What is the leading coefficient? Well, it's the coefficient on the first term in standard form. The second thing that I want to point out is n. N is the degree of our polynomial. And just so we're super aware of what it is, it's the largest exponent. So our two very important things here are our degree, which is the largest exponent, and then the leading coefficient, which is the coefficient on the term with the largest exponent. So if we look at this example, what is our degree here? And what is our leading coefficient? Well, our highest degree is 3. And the coefficient attached to the term with the highest exponent is 2. What's the degree and leading coefficient of this second one? Example. Well, our largest exponent is 70. And the coefficient attached to that term is -3. Awesome. So that is standard form of a polynomial. Next up, definition. This is going to seem unrelated, but we're going to wrap it back around. The real roots, or zeros, we also call them, of a function, this is any function, not just polynomials, are the real solutions to the equation f of x equals 0. So let's think about this a little bit. F of x equals 0 is where the output of our function is equal to 0. Output is associated with y. So this is asking where our function runs into the line y equals 0. What is the line y equals 0? It's the x-axis, right? So it's where our function intersects the x-axis. What do we call that? X-intercepts, right? These are our x-intercepts. Another fact that I would like for us to carry along with us. Remember, x is often our independent value, but sometimes it's not. So let's say we had a function g, and instead of using x as our independent value, we had t as our independent value. Just a note here, solutions to g of t equals 0 are called t-intercept. Oop, squeezing it in. All right, definition. Now that we've talked about roots really briefly, how are we going to use this? Well, the root form of a polynomial with n roots, and we're going to call those n roots R1, R2, R3, all the way up to Rn minus 1 and Rn. If n was 6, then we'd have R1, R2, R3, R4, R5, right? 6 minus 1, and R6 is f of x equals a times x minus R1 times x minus R2 times x minus R3 all the way up to x minus Rn minus 1 and x minus Rn. So this has one of these sort of parentheses units for every root, where a is a non-zero real number called the leading coefficient. Okay, so let's look at root form and how it relates to standard form of a polynomial. All right, so let's look at a couple of examples with this. So give the root form of a polynomial with roots -4, 1, and 2, such that f of 0 equals 24. All right, let's check it out. So we're looking for f. We know that we have 3 roots. So our root form, our general root form looks like this, right? We have our leading coefficient. We never want to forget the leading coefficient. That's a mistake that is made pretty often. We have x minus our first root, x minus our second root, and x minus our third root. We have 3 roots. So we have 3 factors. What are our 3 roots? Well, they're literally listed out for us. So we have x minus -4, x minus 1, and x minus 2. Can we rewrite this in a simpler way? Yeah. Minus a negative is positive. Awesome. So, how do we find our leading coefficient? We've just been given f of 0 equals 24. So, what can we do? Well, this tells us that when x is 0, then our output, f of x, is 24, right? So, let's plug that in. F of 0 equals, we've replaced x with 0 on this side, so we have to do the same thing on the right side. So we have 0 plus 4, 0 minus 1, and 0 minus 2. So we know that f of 0 is equal to what? 24. So we have 24 equals a times 4 times negative 1 times negative 2. So we know 24 equals a times 4 times negative 1 times negative 2 gives me positive 8, which means that a, we divide both sides by 8, we get 3. So we plug that in for a, we get 3 times x plus 4 times x minus 1 times x minus 2, and that's my polynomial. Okay, second example. Give the root form of g of x with roots -3, 1, and 1 that passes through the point -1, 20. All right, let's do the same thing. So we're starting out with g of x. Our regular root form is a, and then there's one factor for each root. How many roots do we have? We have 3, so we're going to have 3 factors. R1, R2, R3. What are they? Well, we have x minus r1 is minus 3, so we can go ahead and write that as plus 3, right? Minus a negative. Then we have x minus 1, and then we have another x minus 1. But instead of writing x minus 1 a second time, I'm going to choose to condense them and just write squared, right? I know that this is equal to x minus 1 times x minus 1. Okay, so now all that's left is finding a. We don't want to forget to find a. In order to find a, we need to get rid of all of our other variables, so we can do that by plugging something in for x and g of x. What do we have? What kind of information do we have here? Well, we know that when x is -1, then y is 20, right? So x is -1, -1, -1. The output of g at -1 is 20. So we have 20 equals a times -1 plus 3, which is 2, times -1 minus 1, which is -2 squared. So we have 20 equals a times 8. We solve for a here. We divide both sides by 8. We get a equals 20 over 8. That reduces to 5/2, also known as 2.5. So our final equation is g of x equals 5/2 times x plus 3 times x minus 1 squared. Let's talk a little bit about how root form and standard form are related to one another. So here's the standard form of one polynomial. P of x equals 2, x to the 4th, minus 3x cubed, minus 24x squared, minus 8x plus 3. And here is the root form of the same function. So this is the same function, 2 times x minus 1 times x plus 2 times x plus 2 times x minus 4. Okay, so again, these are the same function. We don't have to know yet how to find the root form from the standard form. We will learn about it later in the semester, but right now you don't have to worry about that. I would like for us to notice that the leading coefficient here is the same. We have the same leading coefficient for both forms. That's not a coincidence. That will always be true. We have the same leading coefficient whether we're in standard form or root form. So again, the parts of root form we have are the leading coefficient and then the roots, which we have here. Each of these sort of parentheses units are what we call a factor. And the way we use factor is, in this case, here, remember in root form we had x minus the root. So here we have a factor of x minus 4 and a root of 4. Lots of people will get into the habit of sort of switching these and saying, oh, I have a root of x minus 4, or oh, I have a factor of 4. But we have a factor of x minus 4 and a root of 4. So how can we see that these are roots? So remember, our definition of root is where the function is equal to 0. So remember, we've looked at this with quadratics a bunch, right? Whenever we're trying to solve for 0 in a quadratic, we split it up, right? Because we know if one of the two factors is equal to 0, then the whole thing will be equal to 0. We want to use the same technique here. So we want to figure out where each of these factors is equal to 0. So x minus 1, where is x minus 1 equal to 0? Where is x plus 2 equal to 0? Where is x plus 2 equal to 0? And where is x minus 4 equal to 0? Well, we solve each of these. We get x equals 1, x equals negative 2, x equals negative 2, and x equals 4. These are my roots. So we have the roots 1, negative 2, and 4. Okay, so something else we can notice, a different connection that we can make between root form and standard form. If I were to multiply all of these together, let's think about if we had a quadratic. If I multiply these two terms together, I would have something that started with x squared, right? Then if I added in this factor and I multiplied by this guy as well, the largest term would have that x squared multiplied by this x, so we'd have x cubed. If we add in this last factor, then we'd have another x, so we end up with x to the 4th. So I would have x to the 4th, right? X to the 4th is my degree, because this is my largest exponent. So what can we take away from that? Well, our degree is always going to be equal to the number of factors we have. And because every factor is connected to a single root, then this is also equal to the number of roots. This is going to be very useful for us. Okay, definition. So the number of times a root appears in the list of roots, R1, R2, R3, etc., all the way to Rn, is the multiplicity of the root. So let's do an example with this. Let's say we have f of x equals 3x minus 1, x minus 1, x plus 2, and x plus 5 cubed. Okay, so first of all, is this in root form? Well, the only thing that looks different from what we've seen so far is this guy. But that's okay, right? Because that is short for x plus 5 times x plus 5 times x plus 5. So this is still in root form, just a little bit condensed, which is totally fine. So what are our roots here? Let's write out the list. This factor is going to give me a root of 1, right? Remember, we have to flip the sign because it's x minus the root. This one is also going to give me a root of 1. This one is going to give me a root of what? Negative 2. Again, we have to flip the sign. And then this one is going to give me a root of negative 5. And then there's 2 more for the other 2. So how does this tie in with multiplicities? Well, let's find the multiplicity of each root. So the root at x equals 1 has the multiplicity what? Well, how many times does it show up in this list? 1, 2, twice, right? Has the multiplicity 2. Root x equals negative 2 has multiplicity, I'm going to shorten it, what? Well, it only shows up once, so it has a multiplicity of 1. And the root x equals negative 5 has multiplicity what? Well, it's in our list 3 times, right? 3. So each of our factors is kind of accounted for. So we have the 2 that are 1, we have the 1 that's negative 2, and we have the 3 that are negative 5. And we know that all of them are accounted for by our multiplicity. So what can we say about the sum of the multiplicities? The sum of the multiplicities it's equal to, well, the total number of roots. But what is the total number of roots? It's also our degree. How is this helpful for us? What is this going to help us with? Okay. Let R be a real root with multiplicity m. If m is odd, the graph crosses the x-axis at x equals r, and the graph looks like x to the m where it crosses, if m is even, the graph bounces off the x-axis at x equals r and looks like x to the m where it touches the x-axis. Okay, so what the heck does this mean? Let's look at a couple of examples. So first example, let's say we have f of x equals negative x plus 2 times x minus 1 times x minus 1. Well, this means we have the roots negative 2, 1, and 1. The graph of this function, you don't have to know how to graph these yet. We will do that later in the semester, but as of right now, we just want to look at the graph and see how it relates. So 1, 2, 1. So this graph looks like this. I'm going to look at 1 first, right? We have a root of 1. Again, real roots are our x-intercepts. What's the multiplicity of 1 here? Well, it shows up in our list of roots twice, right? So this has a multiplicity of 2. It's bouncing off the x-axis, and it kind of has a parabola shape, right? Parabolas are the shape of quadratic functions, which are x squared. Looks like x squared, right? Multiplicity 2 looks like x raised to the 2. Our other 0 here is negative 2. Negative 2 in our list of roots shows up once, so we have a multiplicity of 1. And if we were to look just at this section of the graph, if I zoom in on this point, it's just passing straight through, not doing anything funky. It looks like a regular old line, right? Looks like x. So it looks like x to the 1, which is equal to just x. Right, so multiplicity of 1 looks like x to the 1, or a line. Multiplicity of 2 looks like x to the 2, x squared, which is a parabola. Let's look at another one. Let's say we have f of x equals x plus 3, x plus 1 cubed times x minus 3. So what are our roots here? Well, we have negative 1, 3 times. And positive 3. So this graph is going to look like we have 1, and then 1, 2, 3. This graph looks like this. We have a root at -1. We also have a root at 3. What is our multiplicity of the root -1? How many times does it show up here? It shows up 3 times, right? We have a multiplicity of 3. What is the shape of this graph? This kind of looks like a cubic function, right? Looks like x cubed, right? Again, that lines up. Our multiplicity is 3. It looks like x raised to the 3. And again, at 3, we pass straight through. So we have a multiplicity of 1 because we look like x to the 1, or x. Okay, we are going to use this information, use how these look, to figure out the equation of polynomials given the graph. So let's look at our lab manual really quick. This is the section Equations of Polynomial Functions. So if we look at this first one, how many roots do we have? Looks like we have x-intercepts here, here, and here. So what does that mean about our roots? Well, we have a root at -5. But what do we notice about the shape of the graph at -5? Kind of looks like a parabola, right? So parabola is x squared, so that means -5 shows up twice. When we pass through -1, we're going straight through, right? It looks kind of like a line. So -1 shows up once. Then we get all the way over here to 3. We have kind of a parabola shape over here. So 3 shows up, x squared means twice. So we have 3 and 3. Well, now that we have our roots, we can kind of write the generic form, the generic equation for our root form. We have our leading coefficient, then we have our factor that belongs with each root. We make sure we have enough of them for the number of roots that are there. So we have 2 x plus 5s. We have 1 x plus 1 from this guy. And we have 2 x minus 3, so x minus 3 squared. Now, how are we going to find the root? We've practiced this, right? We find the root by plugging in something for all the other variables. So we plug in something for x and then something for f of x. What do we have here that we haven't used yet? We have this extra point, 0, 2, right? So let's plug in 0 for x and see what happens. So f of 0 is a times 0 plus 5 squared times 0 plus 1 times 0 minus 3 squared. F of 0 we said was 2. So we have 2 equals a times 5 squared, which is 25, times 1 times -3 squared is 9. So we have 2 equals a times 25 times 9 is 225. We plug this in. So a here is 2 divided by 225. I'm kind of running out of room here, so I'm going to move back up here to write the function. So it looks like we have f of x equals, our leading coefficient is 2 over 225 times x plus 5 squared times x plus 1 times x minus 3 squared. All right, let's look at number 4. What are our roots here? Looks like we have -2. How many times does -2 show up? Well, looks like an x squared function, so twice. We continue along, we pass through at 1. How many times does 1 show up? That definitely looks like a cubic function, so that's going to be there 3 times. And then we keep going, we pass through, we get +3. How many times does that show up? Well, we pass straight through, so just once, right? So what does our generic root form look like? Well, we have a, then x, our root is -2, so our factor is going to look like x plus 2. That's going to be squared. We have x minus 1. There's 3 of those, so we cube it. And then last but not least, we have x minus 3. We want to find a. We need to do that by plugging in a point. Looks like we've got one kind of laid out here for us. So we have f of 2 equals a times 2 plus 2 squared, 2 minus 1 cubed, 2 minus 3. F of 2 we said was 16. So we have a times 2 plus 2 is 4. 2 minus 1 is 1. 2 minus 3 is -1. So 16 equals a times 16 times 1 times -1. So a here is 16 divided by -16, or -1. So our function looks like negative x plus 2 squared, x minus 1 cubed, and x minus 3. And that's the function. Okay, that's all I have for y'all today. Thanks for sticking with it.